Hi, welcome to the final simulation summer school session from 2021. Thanks for coming along, everyone. So I'm really happy to welcome Mark Adkins today. Mark's a PhD candidate at York University in Toronto, Canada, and he sort of specialises in quantitative methods, kind of mathematical methods and things like that. So he's going to be taking us through the SimDesign package in R, and I'll just hand straight over. Thanks very much. Welcome, Mark.
Thank you very much. I'm very excited to be part of this. When I heard about this on Twitter, I'm like, I have to be a part of this. It sounds like such a fantastic resource for everybody. Okay, so again, we're going through the SimDesign package today, and all these slides will eventually be available on my website. I made them through the Sheridan package, so they're all generated in R. We got some, magic stuff happening. So like Oliver said, I'm based at York University in Toronto, Canada, and I do specialize in quantitative methods, doing simulation work in a variety of different research interests. So when you do get access to the slides, they're all clickable links, hyperlinks, so you can jump to different parts of the slides that you need. If you need a refresher, you can simply click those and away you go. So a little bit about myself. I am a fourth-year PhD candidate, hopefully wrapping up soon, the next little while, at York University. And my research interests are loosely around open science practices, statistical pedagogy, Monte Carlo simulations, effect size estimation, as well as integrating technology into the classroom. And I've taught a variety of different introduction to R using the Tidyverse short courses, as well as workshops on data cleaning and pre-registration practices. So the creator of the SimDesign package is he's an associate professor here at York University in the same area. He's also an associate coordinator in the statistical consulting service we have at York. And he's also an author of multiple R packages, which are hosted on CRAN, like MERT, MERTcat, and SimDesign and MATLib, and focuses on research pertaining to psychological measurement, latent variable modeling, and computational statistics. Okay, so when I say Monte Carlo simulation, so to make a bit of a baseline, so we're all on the same page what I mean by that, I'm referring specifically to Monte Carlo simulation experiments. That's a very specific type of Monte Carlo simulations. And these types of studies are computer-driven experimental investigations in which certain parameters like population means and standard deviations are known a priori, and they're used to generate a random but plausible sample data. So you can think of it like there's a particular phenomenon of interest that you're trying to model, and we would create these statistical models with different distributions for these variables and try to see how they might relate as you do tweak the model in different ways or certain assumptions are or are not met. And you might have been familiar with doing traditional empirical research where you might identify a particular population of interest that you want to know something about, or you've got particular research questions. You might pick particular attributes that you're interested in, might want to try and measure or find some way. And you might use all the information, maybe construct a theory and say, here's how I think things are going on, or why we saw the information we saw for particular participants. And then we go ahead and collect our measurements, analyze the data to draw a conclusion or answer research questions, or maybe provide evidence towards some particular model or not. And it's always good to keep in mind that data are only ever a snapshot of our subjects. We don't really know what happened behind the scenes or the generative processes that gave rise to the data we observed. We can make guesses or inferences, and that's kind of what we're all doing in inferential statistics. So, pardon me, get caught up on my slides here. So Monte Carlo simulations are not much different than empirical research. In fact, I would argue that Monte Carlo simulations are a kind of empirical research. Well, what they share in common is they all would have a well-articulated research question. So there's something that you're interested in knowing about, and you want to take care to craft that research question so you're very specific about what you're doing. As well as the design of the experiment was also well thought out. So in traditional research, just simply running an analysis doesn't really give us meaning to these numbers that we think they're doing. We have to first design our experiments in such a way that we are eliminating confounds and a variety of different other things that go into research design. And simulation experiments are no different than that. And we need to also clearly outline the assumptions that we're making about the data or data generating processes or mechanisms. One nice thing about Monte Carlo simulations is we can explicitly put those in there, so we can build in that the assumptions are satisfied or not satisfied, and maybe that has a bearing on our research question, the types of questions we're asking. And without each of these pieces, results from a simulation or any research would be inconclusive or worse yet actually misleading, where the results aren't actually telling you the thing you think they are. So you have to have those questions and the design and all these assumptions sort of in place for regular research, and especially so for Monte Carlo simulations. you want to know a little bit more, I highly recommend an episode from the Quantitude podcast by Patrick Kern and Greg Hancock. Episode 23 called Monte Carlo is a fantastic resource to just listen through and get a sense for what's going on. And there is a link to their archive of their episodes. And so to paraphrase, my favorite part of that podcast is this sort of paraphrase for simulations do not replace thinking. So just conducting a simulation isn't going to somehow magically solve some problems or give you an answer to something. You have to put as much care into this as any other sort of traditional research you might normally do. And so this gets a slide all by itself. Just the idea that simulations don't replace thinking. So just doing a simulation for something, like a power analysis or any other aspect of your research that might benefit from a simulation work, isn't going to somehow give it more credibility or make it more rigorous. It's the thought and care you put into designing of those things. So those have to be in place. Otherwise, I'm not sure what you're doing. Okay. So following my own advice for the duration of this workshop, I've got a working example I'm going to be going in and out of, and there's going to be a chance we're going to go into some breakout rooms later. You guys are actually going to try and code some of these things, and I'll be able to hop in and help troubleshoot a little bit. So the research question I'm going to be dealing with today, or we are, is I want to look at aggregate or group level differences between two populations. So I've got a theoretical waitlisted control group, and on the other hand, I've got an intervention group. I want to know if they differ on some sort of quantitative or continuous outcome variable. More specifically, what we're interested in today is we want to examine how statistical power and type 1 error rates, or false positives, of a t-test fluctuate as a function of population mean differences, sample sizes, and unequal variances. So this is where I've sort of outlined where I want to go with these, this particular simulation I'm going to be coding up for us today. And I can't stress enough just how important it is to have the sort of well-articulated research question in advance of actually coding. Because a lot of time can be saved having an idea of where you're going and then sort of piecing through how do you get there and building up your simulation piece by piece so you can get it functioning and working. And you can always, as you'll see later on in SimDesign, easily extend it and make it more complicated however you want. The sky is sort of the limit on that. And with any statistical model or test, there's always going to be many assumptions involved. And as I mentioned earlier, one of the beauties of Monte Carlo simulations is that you have full control over the data generating processes. So you know exactly what the true population parameters are. So you aren't really making inferences in that sense because you know what the population parameters are. And so you can see how they're recovered or how some of these things change as you maybe very systematically vary different assumption violations. You can also make sure that certain assumptions are completely satisfied if they don't pertain to your research question. So pulling that question apart a little bit, I see there's sort of three factors that I'm interested in. The first is the true population mean differences, and I can pick a variety of different levels. So I want to have 0, indicating there are no population mean differences. So on average, the waitlisted control group and the intervention group are performing about the same. There really isn't any difference, statistical or otherwise, because I tell it there is no difference by making it 0. And you can also pick any other level you want, like you pick 0.5 or in your particular substantive field of interest or your study. Maybe there is a minimally meaningful effect size of interest that you want. You can always put that in there too to say, okay, what would be the power of at least being able to detect that's something that's important enough for you to sort of care about in practical terms. The second factor we're going to be looking at is unequal population variances. And when you're doing simulations, you can sort of not quantify, but you can sort of conceptualize how, operationalize is the better word, how you want to operationalize unequal variances. So I decided to go with like a ratio. So if there's like a 1-to-1 ratio between my two variances of my two populations, the waitlisted control group and my intervention group, then they would have a 1-to-1 relationship. So whatever this variance is exactly equal to the other variance. Or maybe I wanted one variance to be twice the size of the other variance and see how that shakes out in terms of my false positives or my statistical power. Or you could just simply put in the exact numbers that you want, whatever you want. It's just the idea of having a clear idea of what you're going after. So I want to somehow capture unequal population variances. So I can either put like an absolute measure or maybe a relative measure like the ratio of one to the other. Sample size is the third factor I talked about in my research question, or I might start with the sample size as small as 30 or 60. You can go smaller or larger, whatever's going to help you get some sort of meaning or understanding of the results of your simulation. And it's always important to stop and think about these levels of your factors that you choose to include, because they should carry some sort of substantive meaning. And I would also argue at least some of the levels, or if not all of them, should have a defensible justification. So why did you choose a population mean difference of 0? Why did I choose a population mean difference of 0.5? talked a minute ago just about why I chose 0, so I can actually assess the false positive rate, because if there are no true population differences between the two means, then any if I collect a p-value after conducting a t-test, any statistically significant result or indicating I reject the null hypothesis would be a false positive, because I know the true population mean, so I can get a sense for just how inflated or close to the nominal alpha level the false positive rate is. And when you're first beginning coding up simulations, you might also start thinking about different these endpoints as anchors. So you're, sort of as baseline measures for where you might to start, and at the other end where you might want to end. So you might have the lowest minimally meaningfully effect size of interest that you want, and then you can go up to some other top end saying when we get to this large, it's very clear that is something of interest or it's large enough for you to particularly care about. The outcomes I defined for us today are statistical power and the type 1 error rate. Bit of a statistical refresher for you. Statistical power is a probability that a null hypothesis statistical test will correctly reject the null hypothesis. So there are true mean differences there, and you're able to detect them with an NHST test. And type 1 errors occur when a test incorrectly rejects the null hypothesis. So that's a false positive. So the test is rejecting the null hypothesis, indicating that it may not be tenable or reflecting anything actually there of substantive interest. And if that is not true, so there really isn't any mean differences, then that will be a false positive. And there are many issues with conducting an NHST and the interpretations of those things, so I'm not going to get into those, just we're going to focus on those two outcomes. I didn't forget to mention at the beginning, if you have any questions, feel free to use the raise hand feature or hopefully politely interrupt me, and I can try and take your questions as they come. Don't mind at all. So the SimDesign package itself, I want to talk a little bit about the structure so we can get a sense for where we're going. This package uses a novel approach to conducting Monte Carlo simulations that I hadn't seen in other packages. And what the design philosophy is, it's going to functionally separate the whole simulation into 3 distinct pieces, where you have one piece to handle the data generation, one piece to do the analysis, and another piece to sort of summarize all the repeated iterations you're going to be doing of that particular analysis. So for R, if you have 1,000 replications, for each 1,000 replications, how do you want to summarize those, that information to sort of get some sort of meaning out of your simulation results? And when you're coding up a Monte Carlo simulation using the SimDesign package, there's always going to be 4 steps that you're going to be going through, no matter what or how complex the phenomenon you're modeling. We're going to go through each one of those today and practice them. Step 1 is creating a simulation template using the sim functions function out of the SimDesign package. And what that's going to do is create a sort of skeleton R script for you that you can sort of fill in just the parts that are needed that you want to sort of customize, but the framework will be there so you don't have to code up everything from scratch. It's also nice to help you understand where you need to be going, what has left yet to be defined by you as a user, and you can go on from there. The second step is creating what's called a design object. So this is kind of one of the control mechanisms that SimDesign does. So you can think of it as all of the factors they're going to be using. So we talked about population mean differences, unequal variances or the variance ratios, and these sample size. And it's going to be like the cross combination or the fully cross combination of all those design levels, so that I have this one object so that each row represents a unique combination of all my levels of my factors. And so what SimDesign is going to do is it's going to slice off one row, then use that for the generating of data and analyzing the data. And once those are all done, eventually they'll summarize it. So what we need to do is after we design this, create this design object. The third step, and the most difficult one for us, is actually defining the body of our Monte Carlo simulation functions. So there's 3 functions: generate, analyze, and summarize. Each one does what their expected name sort of implies. And once you have those 3 objects, there's this other 4th step, the last one, called a function called run simulation. And that sort of takes all these pieces and ties it all together for you. Okay. So first step is generating that sort of structural template. What we're going to do is begin by running the following code in the R console. So if you're following along, I'll sort of show you what I'm going to do. So I'm going to run this sim functions function in RStudio. And so whenever I see this little RStudio icon up there, it means I'm going to hop over and sort of demonstrate something for us. As a bit of a side note before I start that, there's this other optional argument, which defaults to false, set to true, which will also add a couple extra comments inside this sort of skeleton template for us to help guide us through the process of what we need to be sort of including or what we need to be doing in each one of these steps or functions. Okay, I'm just going to paste that right in there. I'm going to give it a file name. If you're doing this within RStudio, one really nice thing is it automatically opens up the script file for us. And if this is hard to read or needs to be larger in any way, please let me know. And so I'm just going to quickly go over this. So it's going to automatically put it in the code to load the library for you. It's going to have this placeholder for the create design. So it's going to give our design object. We've got this little skeleton framework for each of our generate, analyze, and summarize functions. And at the end, the run simulation. So all we have to do, as if it's a small, easy thing, is just sort of populate and fill in each one of these functions. Okay. So the next step after we've created this sort of skeleton framework is to modify the design object. And so this design object, as I mentioned earlier, is how SimDesign keeps our simulation organized and also makes it easy to add levels to existing factors or even add whole new factors on the fly without requiring a lot of extensive modifying of your code. So you might get a simulation working and then realize you need to include another factor, and that might require another level deep of nesting if you're using a for loop strategy, or it might break your code while you're trying to extend it. And one nice thing about this design object is you've got one place to sort of put that in there, and it easily helps you extend your code. Sort of the resulting object it gives you is essentially a table or a data frame, which is a fully crossed design object using all the levels of your factors. And each row, as I said earlier, indicates a unique combination of the levels of your factors. So a bit of tips. So in a minute, we're going to go into a bit of a breakout room to try this. So I'm going to ask you guys to go ahead and try and create that design object or modify it to reflect our research question we're working on today. And what I recommend to you guys doing is picking meaningful factor name. So this is just general good coding or scripting advice. So if you're going to create a variable or an object in R or any programming or scripting language, giving yourself meaningful factor names is going to help you with the readability of your code and debugging later on. So I can't emphasize enough that you should pick something like sample size or n. Between these two, I'd prefer sample size because if someone isn't familiar that lowercase n is indicating your sample size, there may be ambiguity there, they might understand, but being as explicit as possible is going to help because you never know who might need to see your code to learn from it if you're going to be doing open source or code sharing. I also recommend when you're designing the object or your simulations to begin with, start small. I mean, we got to begin somewhere. So what I would recommend is picking just a few levels of all of your factors, or maybe even just one level. So you can sort of get the simulation sort of off the ground and working, and you can sort of tweak it and work on it from there and fine tune it. I also recommend when you're creating this design object to think about all the factors that need to be involved in your simulation. So anything that is going to affect or alter the generation process, the analysis process, or if you conceivably could think of something that might affect how you summarize the data, you might want to put that in there too as a factor. So that way when you're coding your experiment, everything's all sort of included. So again, reminder, the design objects is a tibble. So if you wanted to, you could use the dplyr verbs to subset it or alter it in some particular way and still use it, and it'll still be just fine for the SimDesign purposes. And so this is going to be the first breakout session we're going to get to. So as a reminder, we'll use our research question we discussed earlier to update this create design function at the top of our mcs.r script file. We want to make sure we include all the relevant factors. So sort of list them here again. So we want to do something that captures the population mean differences, unequal population variances and sample sizes, and a reminder to try and pick meaningful factor names. And to begin with, just put a single level for each of those factors just to get us started. Okay, so once we get these breakout rooms all set up, I'll give you guys about 5 minutes, and then we'll call you all back and we'll sort of see what everyone's come up with.
I'll do a random assignment. How many people have got? How many people do you want in each breakout room?
4 or 5.
4 or 5. There we are. Okay, so I'll create those. It's found automatically, and here we go.
I see a question in the chat I can answer when we come back.
Okay, cool. Job done. So, and you want about 5 minutes. So we'll come back.
I got a timer going.
Sorry?
I have a timer going.
Oh, you have a timer. Okay, great, cool. Good stuff. Up on your screen, there's someone's asked for help in room 4, Mark.
Yeah.
Yeah.
Okay, welcome back, everyone. So we were talking about trying to create that design object, and there could be a variety of different ways we could do that. Does anyone have a solution that they sort of came up with, what they've done so far, they would be willing to share?
Sure, if I could do that. Do I just share my screen? Do I have privileges here? Oh, it says I can't share while someone else is sharing, but I could, yeah.
Shall we pause during this part? Everyone, if people are discussing, I can pause the meeting, pause the recording.
See that?
We'll leave it.
Yep.
So there you go. So here we're just writing create design, and then we're specifying some meaningful names associated with each of the lists of single elements for the specifications. Before I actually had variants set up a little differently, but I just followed what you said in the slide.
And you can do it either way. So you can actually put the actual variances or a pair of variances if you want them to differ, whatever you want, as long as you start consistent so you know how to be generated and how to use it later on. So this is where it's similar to what I'll be doing and showing you guys today, but you can do it anyway. It's flexible enough to handle it all. And I see in the chat, you've got a couple of other very similar things. So you got good names on those, and all the relevant factors are included. See one, we've got one for the standard deviation ratio of the two of them. Okay, let's go back to sharing. Okay, so the solution that I decided to use for this was I had something called mean difference, and I'm going to have one level. It's just going to be value of 0 for the first one. I've got sample size and my variance ratio. So again, as long as you have meaningful names and you know how you operationalize those, if you operationalize those as standard deviations, as like pairs of standard deviations. So here's what the first group and the second is going to be, or ratio from one to the other, so that if you have a starting point, you know how to calculate the other one. As long as you know how you're going to be doing it, so you can use that in our generation function in a moment. Okay, so we saw a couple of the solutions people had, and at this point, usually I would ask if there's any other factors you might be would consider that you'd want to put for our research questions. So it may be a peripheral question or something else, another factor you might want to include that we didn't think about to begin with, but I'll sort of save that until we go to something later on. So the next part of the step is our generate function. So I just want to break down a little bit about the anatomy of the generate function. So like every R function is going to have a name, which is provided for us with that sort of skeleton outline, as well as the arguments, which are also provided for us. And the body bit, which is obviously going to be the hard part, because that's where we have to actually program in the data generation process. So what we have here is the condition. So you can think of that as, again, our design object we just created. If we actually created that object and inspected it within our studio, it would be a data frame with just a single row, because there's just one level for each one of those factors. And so what condition is for any particular iteration of our generation for conditions is it's going to take off a slice of one row from our design object, pass it into the generate function, so we can use any of those values or levels of our factors to generate our data. Every one of these functions also has this other object or argument, pardon me, called fixed objects. And for most simulations, you probably won't need those, but there are times when you might have some particular object, like a covariance matrix, you're going to be using to generate multivariate data in some particular fashion. And it's going to be the same for the entire condition. So instead of recreating that object every time you run 1,000 replications on one particular condition, you can create it beforehand, pass it in, and then SimDesign will make sure that every replication will have access to that object, so you can save some computing time so that it doesn't have to recalculate that same thing because it's identical across the entire condition. So that's the general thing. And then when you're done, you want to be able to return some kind of data structure. So you can decide any type of data structure that would be helpful to you. So if you want to capture all the data as a vector or a matrix or data frame or list, whatever sort of useful for you. I think most times having something like a data frame is what people most commonly do. So you got flat two-dimensional data where each one of your columns is going to be indicating some attribute or variable about your subjects. And then each row indicates, one unit, basic unit of analysis. So if you're looking at the subject level, this is like, subject 1, subject 2. If you're looking at country level data, it'd be country 1 and country 2. And you're going to structure that into like a data frame or something else, and then that gets returned. And when we were first generating our data, one thing I like about when we did the create design with that design object is creating sort of a baseline condition, which is sort of well-behaved, where we understand something about the properties of our outcome variables. So we're after false positive rates, and we're after statistical power. So if we put in our mean differences or true population mean differences equal to 0 between our two independent samples, what we can do then is once we finish our simulation, we can look and see what our false positive rate is, because we program in all the other assumptions of our independent samples t-test to be satisfied, then we should get an empirical detection rate, or the number of p-values that are below a particular threshold that we're interested in, like alpha 0.05. We know that should be really close to 0.05. So we can see that with the code we've done for our generation, analyzing, summarizing is performing the way we expected. So we can see that our simulation is working and R is doing what we think we asked it to do, which is a very important distinction. And then from there, we sort of build on and extend our simulation. Okay, so the generate function was deliberately designed to be flexible in terms of those data structures, and whatever you decide to choose on, like a matrix or a data frame, to be returned by that function. All that's important is you know what it is. That way, when you get to the analyze function, you know how to unpack it. Because you could have sent in lists or pairs of sample sizes. So for the first row, instead of it being a single value for the sample size, it's actually a list that contains a pair of values. The first is the sample size for maybe the waitlisted control group, and the second one is for the intervention group. As long as you know how you stored or structured your data, you can unpack it a little bit easier in the analysis function. And so, yeah, it'll help make it a little bit more efficient for your coding. And for our current example, what I'm going to be doing is showing how we can generate some data to conduct an independent samples t-test using our data, and I'm going to create it in long format, but you can create it however you want it. So a couple tips when you start doing the generation function for yourselves is you might be familiar with the R's base R's attach function. There's another function imported or created in the SimDesign package for is capital A attach. And so what that function is going to do is it's going to extract out all the contents of a list object, so a data frame or tibble. Each is actually technically like a list of vectors, and it's going to place them into the environment in which the function was called. So at the beginning of our generate function, we can attach condition like this, and what that's going to do is it's going to take off that one slice of our design object that's currently what condition is going to be inside of. That's what the contents are, and it's going to extract out each one of those columns so we have those names, so we don't have to type in a lot more typing, because let's be honest, we're efficient, we're not lazy, we're efficient for the amount of typing we want to do, and it'll reduce it. So instead of typing condition, $, sample size, we can just write directly sample size. One advantage to that is also makes our code readable. So instead of trying to parse through a really long subsetting operation by using that $, we can just use sample size and we know exactly what we're dealing with, because that's from our design object. It also helps reduce the cognitive load for object tracking, so we don't have to create as many objects. And it also eliminates the need to rename conceptually identical objects. Because in our design object, we've got something called sample size. And if you've ever simulated data using like a nested for loop strategy, sometimes you might have, little n is the name of the sample size, and then within one particular iteration of the loop, you might need to access that, and you might have to call it something else like large n, or you call it sample size. And the more times you have to reference something that's conceptually identical, you got to come up with a new name, and that can be problematic because you spend time carefully crafting and choosing a meaningful name to begin with. It'd be nice to be able to carry that throughout your entire simulation. So by doing it this way, if you get a name like sample size, it's going to be sample size in your generate function. It's going to be the same in your analyze function and in your summarize function. So highly recommend that. One other thing I also want to mention, there's also a nice safety feature with the capital A attach function versus the other one. So I believe in base R, when you use attach, if there is an object that exists that is the same name as one of the contents of your list object, it will actually overwrite it. So if I have a object in R called sample size, and I use attach condition with a lowercase a with something called sample size as one of my columns, it'll actually delete the old one and assume you know that's what you're doing and won't even give you a warning or an error message about that. If you use the capital A attach, what it'll do is it'll check, and if there is a naming conflict like that where something will be overridden, it will actually throw an error and not let you do that. So you can't accidentally overwrite something that you're dealing with. So that's just a nice thing where there's just safety features built in around these things, so you don't have to worry about these very common pitfalls that occur when coding in any language. Well, at least R, because you can just overwrite easily. So another couple of tips here is you want to think carefully about how the data generation would change as a function of the current condition of your simulation. So if we're currently simulating the first row of our design object, we want to see how did the level of those factors change our generation. So for every row where we're dealing with, well, what I'm kind of assuming we didn't really say or specify to begin with is I'm going to be sampling from a normal distribution. Though you could do any distribution, whatever you want, as long as you've got some meaningful or defensible position for choosing a particular distribution. I just chose to stick with normal because it's sort of fairly simple, something people are a little bit more familiar with maybe. But the center of that, where the distribution is, or the location, would shift depending on where the mean is. So what I might have to start is using this R norm. So it's going to randomly sample n equals 30 participants from their unit normal distribution. And it's the unit normal because it's going to be located or centered around with a mean of 0. And my standard deviation, or also variance in this case, would also be equal to 1. So that's how I might generate normal data, normally distributed data from that function. But what I want to do is take that and change that so that it takes advantage of the current level of my simulation or one of my conditions. So I'm going to begin by attaching condition, which is going to give me access to this mean diff variable. So instead of typing condition $mean diff to get access to that, I can just use it directly. I can just put it in there and pass it in as one of the arguments for my R norm function. So to incorporate the idea of mean difference, how I've operationalized it today, is just simply passing one, instead of having a numerical value of 0 in my R norm function, I'm going to pass in that variable, and now I've already incorporated one of my design factors into my simulation. So sometimes it's easy-ish, I don't want to say probably easy is the wrong word. Sometimes one of the ways to accomplish what we're trying to do for simulating our data is just changing one of the arguments of a function that already exists. What else might happen is you might have to deal with logical branching, where what might be needed is different code that would be appropriate in some conditions, but not in other conditions. So depending on the current value of one of our levels, we might have to run a different function entirely. So there's nothing I can do to, well, unless you listened to Oscar's talk earlier, nothing you can do about the normal distribution to sort of make it like a T distribution or something else. So again, if I began with the normally distributed data, unit normal, and I had another hypothetical situation where I wanted to change the distribution of which I'm sampling from. And so in my design object, I've got a variable called dist or factor, and it contains the information about which distribution I want to use. So I'm going to attach condition, giving me access to dist directly. I'm going to start programming in a logical branching. So I'm going to do a test for if the distance current value is normal. So that's my way of tracking to myself, I want to be using the normal distribution for sampling. Then I'll run this code from a normal. Else, if it equals something else, and the distribution is actually T, then instead I'm going to be randomly sampling from the T distribution. And so depending on the level of my factor or how I operationalize my factor, I can either change arguments to functions that already exist to get the data generation that I'm looking after, or I might have to do logical branching and do a different set of code or different functions entirely to get the result and incorporate my factor that I'm looking after. Bit of a side note, there's a lot of helpful data generating functions out there. So base R and stats package has things like the normal distribution, the T distribution, or binomial distribution. SimDesign also comes packed with a lot of other handy distributions from which you can sample from. So things like the Hedrick and Vail Morelli are also used something called the moment matching technique, where you can specify the first 4 or 5, I can't remember, moments. We got the mean, the variance, the skewness, and the kurtosis to have non-normal data, or at least univariate non-normal data. It also imports the multivariate normal from the mass package, I believe, and the multivariate T. And you can also have like a random integer if you want to make sure that's there. So there's a lot of built-in functions here to help you generate the data that you need to sort of model the phenomenon you have of interest. Okay. This is going to be our second breakout session. We're going to give ourselves at least 10 minutes, maybe a little bit more, depending on how much time we need. Well, we're actually going to go and try and generate our data using the design objects that you guys have already started working with. So what our goal here is we want to use our factor levels from condition. We want to generate 2 normally distributed samples and save them into some kind of tibble or data frame that we can be used later on to conduct our t-test. To be clear, the step we're going to be trying to do is I recommend using the capital A attach function on condition. You don't have to, it's helpful. You want to make sure that you're incorporating all 3 factors, because each one of those factors we're dealing with are the true population mean differences, the variance ratios, or however you operationalize that, and the sample sizes, or whether they're the same or whatever it is. All those 3 need to be incorporated so that way, whatever the condition is, it's going to be generating the data contingent on those current levels. When you're done, save them all into some kind of data structure. It could be a data frame or tibble, it's probably convenient, but you can do whatever it is that you want for that one. Okay, so now we'll go back into breakout rooms again, and we'll see what we come up with. And I'm going to hop around a little bit more to help troubleshoot. Okay, welcome back, everyone. You guys did a good job through that. So again, here's just one possible solution. So I decided to do it was I took my generate function. I began by attaching my condition. And I sort of set my sort of control group variance, because I decided to operationalize variances or difference between them as a ratio from one to the other. So as long as I choose one particular variance, the other one is just defined by being the ratio of the 2 of those. I decided also sort of generate them in long format. So I've got one variable capturing the group level information. So my group 1 or my control group, and group 2 for my intervention group. And so what I'm going to be doing is just repeating this value of group 1 the number of times with my sample size, and then going to repeat the unique value of group 2 for the number of times with my sample size. And so when I run this particular code, what you can always just pop into the R console to make sure it's doing it right. So the first, in this case, 30 values would be group 1, and the next 30 values would be group 2 to indicate group membership. And then I took my score or my outcome variable, whatever it is for this example, and I randomly just randomly sampled data from the normal distribution using my sample size. And I took my particular variance that I've got here, and I took the square root. So again, I've defined things in terms of the variances as a rate. The cats are causing havoc, apparently. So so what I did was, so since I defined things in terms of the variances, if you're familiar with the R norm functions, it wants the variability as a measure of standard deviation. So it's the different scaling. And so I took the square root of them to make sure that I'm doing my data the way I expected to be doing it. And I decided to not stipulate or, explicitly write in what the mean was. It's going to start with a mean of 0 as the default value for our norm. So the first distribution is going to be centered around a mean of 0 with a variance equal to the square root of my control variance, which will also be 1. And then my second sample, it's going to use the same sample size, because I didn't talk about different sample sizes in my question, but you could have. And it's going to be centered around the mean difference. So if the first one is centered around 0, then the second one, by definition, would be exactly that much of a jump up or location shift would be equal to the mean difference. So if the mean difference was 0, both samples are going to be centered around a value of 0. And this one is going to be, the variance of this one is going to be the ratio. So I'm going to take my design factor that I've got through a condition, a variance ratio. I'm going to multiply it by whatever my control variance is, and then to get the square root of that, again, scale it back to the scale of a standard deviation. And so I'll put these all together, and then they're going to be saved into a table. So when I'm done this, I should have 2 columns, one called the group and one called score, or it could be value or outcome. You probably want to give it a better name than that. And then it's going to be returned at the end of my generate function. So as one of our group pointed out, writing these functions can be hard unless you have a way to actually test them and see, okay, is it working the way I'm doing it? Am I getting warnings or errors that I need to sort of troubleshoot and get the generate phase working properly before we proceed? And how I recommend doing that is just taking a slice from your design object. So what I'm going to do here is just get a subset and grab off the first row. In this case, it's the only row of my design object. And then I'm going to pass it into the generate function. And then I decided, because of how I operationalize my variables, so that I've got an independent variable and my dependent variable in 2 columns. I grouped it by group. And then I decided to give myself some summary statistics so I can look at the mean of my outcome variable, the sample size that was used, and the variance for my sample. So group 1 had a mean of 0.089, so kind of close to 1. And group 2 had a group mean of negative 0.19, so again, fairly close to, a mean of 0. The sample sizes are both 30, because this indicates, as I just said in my design object, it's just going to be 30, so it's going to be identical sample sizes. And then my variances are 1 and then 0.6. So again, reminder, these aren't going to be exactly our population values because it's randomly sampling, so there's going to be noise. And our sample means, unless we sort of get practically infinite sample size, it might be exactly equal to the population means that we're after. But we can do this little trick to take one piece of our design object and pass that into our generate. Very first argument it's expecting is our design, our current condition it wants to simulate data from. And we can get that from just grabbing a row any way you would normally subset your design object. So that can make sure that our design is working the way we expect it to. So to the next part, pardon me, is the analyze function. And if you first ran that sim functions, you pardon me, generate the skeleton outline to help us work through creating a Monte Carlo simulation. This is what it'll look like. And you're going to see something familiar. We've got the condition and we've got access to whatever fixed objects are currently available for this design condition, or all of them technically. And we've got one additional argument called dat. And so dat is going to be when we call to generate whatever data structure you decided upon to be passed and returned from the generate function, that will automatically be passed into the analyze function for us. So we have the current condition where we are using for our simulation. We've got the data that was generated, and if there were any fixed objects, if it was applicable, they'd also be accessing to us here. And this is where we would run some particular analysis. We'd want to extract out any quantity of interest and save it as a named vector or a list, and then that gets returned. So things to keep in mind when we are completing this function is we're going to be using that data we generated from the generate function. We want to perform some particular analysis. So if it was a between subjects independent samples t-test, then we got to think, how will we actually do that? What function might we need to compute that test? We want to be able to extract out our desired results. So if you're not sure what I mean by that, we got to think back to our research questions. What are our outcomes of interest? What am I trying to use the simulation to help me figure out? And I wanted to know about the false positive rates and the power for particular conditions. So what I'm going to need is a p-value. So we're going to connect t-test and at a minimum, at least pull out that p-value. And we want to, again, structure them into like a named vector or list and then return that list or data structure. So in the similar spirit to the generate, you'll notice pattern's got the same design philosophy across these three, is we want to make sure that there's any factors that might alter how we analyze our data that's included here. So the research question might be how different assumptions might be violated and what happens to a particular outcome. So that sort of pertains to the generation phase. But you might also say, what if you fit different types of models? Maybe you've got one model that you know is like the correct correlate of the population generating mechanisms. You can put that in there, but maybe you wanted to do a different model. What if you had a misspecification or different types of misspecifications? You can put those in as a design condition as well. And so if you did those won't affect how you're generating your data, but they're going to affect how you're going to analyze the data. So we can see some of your research questions can be about the generative processes or phase. They can also be about the analysis itself. And in this current example, there isn't any part of our design condition that's going to be affecting our analysis. So it'll be sort of straightforward. So whatever we code up to conduct a t-test, extract out our p-value, which is our quantity of interest, we won't have to make reference to our condition. So again, if there were factors, you'd be asking yourself, do I need to be using logical branching to sort of run different separate parts of the code or different analyses depending on the current condition you're simulating data for? Or can that be accomplished just by changing or passing one of these condition values as a new argument to an existing function? There's one big tip here: whenever you're coding, I recommend not using what's kind of sometimes referred to as magic numbers or things you expect as a constant for two reasons. One, you might leave your code and come back in 6 months and forget what that number means. You might have had a good rationale for why you chose this number, why the mean difference is 0 here, or the control variance is 1, or whatever it is. And you might not always remember that later on. So hopefully you left yourself good comments, but also maybe giving yourself a good descriptive object and storing that value in there. So instead of, like in the last example, when you've got the control variance of 1, I know it's the variance of my control condition. And it's also nice because that helps us easily extend our code later on, because if we want to programmatically change something, say maybe reviewer 2 points out a fact that I should have included in my simulation, which I didn't think about, by putting it this way and actually coding in the name of an object, all I really have to do is just delete that sort of initialization of that control variance, and our code's already going to work as long as we have a similarly named object within our design object. So the take home here is try not to use just numbers there. Try to give it an object name to help your code and anyone who might be using your code, including future you. Yeah, so that's what I was just talking about there. I got ahead of myself. So for our third and last breakout section, what we're going to be doing is we're going to use that data object that we got from our generate function called dat, and we want to conduct a t-test and extract out the p-value and any other maybe statistic that you feel might be important. Because sometimes when you are conducting a simulation experiment, you are focused on your outcome, which you should be. You have to make sure that you are accurately and completely capturing the information you need to answer your research question. There might be other extra peripheral statistics that might be of interest. Maybe you want to know if there's bias in the estimation of other parameters that you didn't think about to begin with. So sometimes you might want to extract out a lot of extra information just in case you need it, because there's ways of saving all the results from your analysis function. So if you are replicating each condition 1,000 times, may be useful to save the p-values and the estimated mean differences and all these other information from the t-test 1,000 times. You may want to look at them later on or do a different type of summary because a reviewer asked you something about part of your model or your simulation. So it's also nice because then you don't have to rerun the entire simulation just to accommodate something else. Because I remember for my master's thesis, it took using distributed processing or parallel processing, it took about 2 weeks to run my whole simulation. And if I had to rerun that thing over again, just because I forgot to include something, it'd be nice to save the results or extra information, and maybe that saves you some time down the road. Unnecessary, but helpful advice, I think. So that's what we're going to do. So we're going to hop back into the breakout session rooms. We're going to give ourselves another 10 minutes or so, maybe a little bit longer. And our goal here is to take the data that you created or passed on from our generate function. So however your groups have decided to operationalize that to get a data frame, I use like a long format. You guys might have used 2 rows, each one capturing a different sample. Whatever it is, take that, conduct an independent samples t-test, extract the value, and sort of put that in the return object. So when you guys are in your rooms, I will go ahead and start the timer and I'll hop around and help as needed. Welcome back, everyone. Everybody found that the analyze step for this particular research question for this example is a little bit more straightforward and a little bit easier to code up than the generate function. But I think everybody sort of got to some sort of solution for themselves. And so one solution I'm going to show you that I went with was actually again anticipated by one of the audience members. So when you do the t-test in R, if you're not familiar, by default, it assumes that the variances are unequal, or does the Welch correct the t-test. And nothing about my research question said anything about which type of those independent samples t-test should I use, the Welch corrected or the regular one. And so what I decided to use was the default Welch corrected. So the var.equal argument is going to be equal to false. And what I put up here is I create an object or a placeholder. So instead of just a value of false, I put in a variable name that I might be used if I want to later on incorporate that into my design to change how I'm analyzing my data. So I want to do maybe both the regular t-test and the Welch t-test to compare how does power change under the same conditions, just whether I'm doing the correction for unequal variances or not. Maybe that's of interest. Maybe that's a nice little extension. And so by putting in here, I got that. So I'm going to run the t-test. Since my data was in long format, I'm going to take my dependent variable. And it's going to be predicted by or explained by my grouping variable. And it's going to take the object dat that we created from our data, our generate function, and that'll be passed in as the data for the t-test. And you could extract out just the p-value, but I'm also kind of a big fan of the tidy function from the Broom package, which is a way of taking model results and sort of packing it nicely into a nice data frame for you for easier managing and extracting. So if you're not familiar with lists and pulling out different arguments of those, it's nice because it can pull out a lot of extra information. So in there, I'm going to get the estimated mean differences, the sample means, I'm going to get the p-values and a variety of other statistics that might be useful. So what I'm going to do is I might not know what I need later on, but I know for sure at least need that p-value. So I'm going to use this tidy function to pull out all that information for me because now I have that so I can use it later on and maybe re-summarize my data. Again, meaningful names is going to save you a lot of heartache and troubleshooting later on. And so by default, the tidy function, the names of the columns in the data frame it passes back are sort of supposed to be generic to handle a lot of different models. So for instance, there's one parameter, the 6th column, which is called parameter, which gives me no indication whatsoever what's actually in that column. And when I look into that, I see, okay, that's actually the degrees of freedom for my t-test. So what I'm doing here is I'm just going to rename some of the columns that aren't so helpful to me so that I know when I go to summarize my data, I've got meaningful names to help me sort through the results. So the first is this going to be my estimated mean differences. I want to have the sample mean and the for first sample and the sample mean for the second sample. And then that one called parameter is going to change to be degrees of freedom. So now I've got my results extracted from my t-test or my test results object. Rename these things to make sure they're meaningful for me so that I can use them a little bit easier in my summarize function. I'm going to pass that final data structure, which is just going to be a data frame, back as my return object. You could also have just pulled out the p-value like this. We could have just said p-value equals, go to my object called test results and extract out my p-value and then save that as a return object and then pass that back. So that's all we needed to do to answer the question we set out to do as far as false positives and the, the power for each one of my particular conditions. So at a minimum, at least get that one. But again, I recommend collecting extra because it might save you having to rerun your entire simulation again to get something that you had available and we discarded because we didn't know we needed it. If you're curious a little bit about the Broom package and the tidy function, they've got a nice little vignette that talk about all the different models that are available that this tidy function will work on to extract out information and how it does it. So you just run that same function tidy on different model objects and it'll pull out and make sure it condenses it down to a nice neat data frame for you. So that does save some time and I like that particular approach. Next up is our function for summarizing. So summarize. So you'll notice, again, a lot of similarities where the very first argument is always going to be that condition or the condition we're simulating data for. Results is going to be the object that was passed, well, not quite the object that was passed back from our analyze function, and any fixed objects as appropriate. So what I want to highlight here when we think about how we want to summarize our data is our function only sort of has access to the results from our analyze function. And what it's going to do is repeat that. Say, for instance, we wanted to repeat each condition and simulate the data 1,000 times, analyze our data 1,000 times, and pull out 1,000 quantities of interest, in this case, p-values. And so what our result object actually isn't just what's passed back from analyze. What it's going to be is like a data frame that's going to have as many rows for the number of replications we have, and as many columns as the number of quantities of interest we pulled out. So if we only pulled out p-values, we'd have a data frame with 1,000 rows and a single column called p.value. In the approach I had a minute ago with the tidy function from the Broom package, I would have 1,000 rows, but I would have a new column for each one of those statistics that I pass back that I might need. So I can now have access to them within my summarize. So this summarize is a way of saying, again, for one particular design condition that I've simulated 1,000 times, and I've now got all that information, all those quantities of interest, and I can summarize them in whatever meaningful way to help me answer my research question. And we'll also note that we do have access to the current condition in case you needed that. Usually, I find you're probably not going to change how you're summarizing your data contingent on the condition. But if you've got the population parameters you used to first generate your data, you might need those for some of the summary statistics for things like bias. So if you've got your true population parameter values set in your design, in your condition somewhere, and we want to calculate the bias to see on average how much of our estimates are different from the true population mean difference, we can do that, and we're going to need access to that. So that's why condition is sort of available or exposed to us here. So we can use that to calculate things like a bias. Yeah. So the point here is having a clearly articulated research question sort of pays off again in this example. So if we had clearly identified our outcomes of interest to begin with, so again, what I'm interested in is my false positive rate and my power for each particular condition, then I should have some sense, or a very good sense, of what I need to summarize, what information is going to be passed back as from our analyze function or all of our analyze functions for one condition, so that I know how I want to summarize it. Right, so then we also do that for summarizing them by having a set of them. We want to make sure that we can carefully summarize them to avoid errors, because it's another very common spot where I think the best way to say that is a lot of errors have been traditionally come up. So if you're trying to manually code bias for yourself, you got to take the correct population parameter and make sure you're getting your sample estimates or the average sample estimate of whatever you're doing to make sure that you're making the appropriate comparisons and divisions so you are getting the answer you think you are asking R to do. One nice thing about the SimDesign's framework of having the generate, analyze, and summarize being functionally distinct from each other is that pardon me, it's a little bit easier to not accidentally overwrite some of the results. So if you've done for loop strategies for simulating data, one common recommendation for you is to pre-allocate an object to hold all of your results. So you might have, if I'm doing one condition with 1,000 simulations in it, I want to pre-allocate a memory space like a data frame or a vector that's got 1,000 rows, and then each iterative of my loop, I make sure I go up and save it into the appropriate location. doing it this way with SimDesign, what it's going to do is it's going to handle all that sort of data management aspect for you automatically. So you can't accidentally overwrite something to the wrong position, especially if you're nested within a lot of for loops and are using names like I, J, and K for your counter iterations of the current value of your for loop. Maybe you accidentally wrote an I and a J and it's hard to spot in your font, so you're accidentally overriding some of your results you didn't mean to, and R is not going to throw an error because it's a perfect syntactically valid code you typed in. It doesn't know that's not what you meant. R is going to assume that you know what you're doing. And one nice thing again about the SimDesign package is it's going to handle all that data saving and summarizing for you, so you don't have those common errors that creep in with simulations. And personally, even using SimDesign, whenever I sit down to write a simulation or start playing around with something to maybe clarify a concept that I learned recently, writing the Summarise function is where I encountered the most trouble and had the most trouble debugging it. So the key that sort of helped me is I got to think again, how do I want to condense down information, or summarize, as clearly the name implies, all those statistics I extracted. So keeping in mind that I've got my results object within the summarize function is going to be the number of rows for the replications I've got, and each column is the number of quantities of interest that I told Analyse I need to save for later so I can use them in the summarize step. I got to think what the summarize function is going to do is it's going to take one particular condition, so the first row of our design object, and I need to take those 1,000 replications and condense each one of the quantities of interest that I'm after down into a single number. So it's thinking in like shrinking them down and summarizing them all that way. By the time I'm done, I've got a single vector or a data frame with just one single row on it. So that's like my end goal or the data structure I'm aiming towards. So whatever I got to do to summarize my information so I've got that type of structure, that's how I know I've done it right, and SimDesign can handle everything for you. And that's sort of what my next point was. So it's also worth noting that computing complicated summary statistics is another easy place to make programming mistakes, because putting a parenthesis on the wrong spot should have been around a different argument and not where you put it is, again, something that might be syntactically valid. So R understands or thinks it understands what you're asking, but that's not what you meant to do. They can be notoriously hard to spot and debug, especially if you're computing particularly complicated summary statistics. So to help, SimDesign has some built-in summary functions for you that are less error-prone in the fact that they've been already tested rigorously to make sure that they're going to be getting what you think you're asking for. So you can customize and write your own summary functions and do it all manually. It's open and flexible to do whatever you want. These are there to help if you need. So in the article that Phil and I had published, which again can be linked through here, there's a lot of metastatistics functions available to you in the SimDesign package. So if you are trying to compute the bias of some sort of estimate, you might not know exactly which type of bias you want. Is it just bias, like in some sort of traditional sense, if there's such a thing, or do you want a relative bias? So I want to know on average, how different are my sample estimates for my population mean, in terms, scaled in terms of your parameter, your sample estimates. So instead of it being a black box trying to guess what this bias or what type of bias is it doing, you can go to the table and check the definitional formula saying this is the type of bias, this is what's after, so you can be sure that you're calling the right function and expressing the right type to make sure you're getting the right meta statistic or summary statistic that you're after. And so there's a lot of very common ones like root mean square error approximation and so on. I'm not going to list them, but today what I'm interested in is this EDR function, or the empirical detection rate. And that's going to again get the proportion of cases where my p-value is less than alpha. So it's going to go through each one of my conditions and give me that proportion of them. So we're done with the breakout rooms for today, but I'm just going to show you the solution that I sort of put in. I think I saw this elsewhere in people's code today. Is again, we've got the condition, our results object is again that number of replications by the number of quantities of interest that we've extracted. And today, all I'm interested in is the p-value, although I do have access to a lot of other information there because I did extract that in my Analyse function. And I set the alpha rate to be 0.05, and I put it in here as the name of an object so I can possibly systematically change or vary it depending on the condition that I'm after. And so my EDR function just requires two arguments, a list of p-values. So I'm just going to use my results object. I'm going to subset out one particular vector. It's going to be my p dot value, and then we're going to compare it against my alpha rate of 0.05, and this all is going to be saved as a data frame and then passed back. So again, this summarize function is going to be called on every condition or design condition from my design object. And you can include as many summary statistics as you want in here. The sky's the limit for what you want, as long as it sort of help you for clarifying why you even sort of are running the simulation to begin with. But even now, we have to think carefully about what our results even mean. So yeah, I included something called the empirical detection rate. I think that's what I'm after to answer questions about false positive rates or power. And so what according to that table 1 I showed a moment ago, what we're calculating is the proportion of our simulations within any or each specific condition, and finding out the proportion of p-values that were less than or alpha 0.05. So for any design condition where the mean difference is equal to 0, then the EDR is actually going to be our type 1 error rate or false positive rate. Because we know at the population level, because we programmed it ourselves, there is no differences between the means or the random the normal distributions we sampled from. So any p-value that is less than alpha rate, or we would reject the null hypothesis, is in fact a false positive rate. We know that because we programmed it to be so. So for any of those conditions, that's our false positive rate. That's one of the outcomes I was hoping to get out of this. And for any of those conditions where the mean difference does not equal to 0, even if it's by like a very small amount, it doesn't matter. As long as they're not 0, that means there is a population mean difference because we coded it that way. Then this same code we did right now for the empirical detection rate is actually going to be the power or the true positive rate, where we have rejected the null hypothesis, and that does in fact reflect the conclusion we should have made about the population, because we know the population means are actually indeed different from each other. So the last part, the step 4 from our SimDesign, using that for constructing our Monte Carlo simulation experiments, is we got all of our necessary building blocks. We got our design object, we've got our generate, analyze, and summarize functions all done. And now we just need to use this run simulation function that's going to do a lot of the heavy lifting and background work to do these things in an error-free way. So again, go back to our roadmap. We create our design object, and we have some way of generating data that's going to give us back some data structure. Today's example, we pass back a data frame. We want to analyze that. We want to take in those data frames, analyze it, or perform a t-test and extract out some particular quantity of interest. Today was a p-value or extra pieces. And then we want to repeat that process a certain number of times. Maybe it's 1,000, 2,000, or 3,000. And for every one of those conditions and those thousands of results, we want to summarize them in some specific way. And this run simulation is going to take all these pieces and put it all together for us. And so as it stands, our skeleton that was generated for us automatically from the sim function is actually able to be run immediately. So the core components you need is a design object. We created that. So we're just going to say the object name is design. How many replications you want to do. To begin with, we're going to start small. So we could have put in 10,000, whatever you want for a number of replications. You can also drop it just to see if your code's working. Maybe drop it down to 100 or even 10, just to see if there's any errors that creep up. Then we have to tell the run simulation function, what's the name of the function that we defined that's going to be used for the generation process, which function is going to be used for the analysis process, and which function is going to summarize our data for each condition. And then optionally, what I also put in there is a file name that says when you are done these results, I also want to save them. So it's going to save them in an object locally in your R environment, but I'd also like to save those to a particular file externally for different reasons. And I decided to give it a name of SimDesign, my first example or first experiment. And then I used a Liberty package to do it today, so it depends the date into the file name. So maybe if I run this again tomorrow, it might help me differentiate between, was this the first simulation I ran, or was it the second time? Sort of help ambiguity. Or avoid, pardon me, ambiguity. Okay, so what I'm going to do now is actually hop over to our studio and run this. So that is my template. But I'll just quickly create all of our objects. Okay, it says I could not find that. So like a rookie, clearly I did not actually load the library to access these functions I needed. So I'm going to quickly attach Tidyverse, Broom package, to the SimDesign that I might need. I've already created all of my objects. So now what I'm going to do is actually I can just show this here as well. Is I'm going to do this run simulation. So this is exactly the code as I typed there a moment ago. And so I'm going to go ahead and run that. An object not found, of course. The troubles of live coding things. Okay, so let's create our design object. going to remove some of these to make it a little bit faster, not all of them. That would not help us. Okay, my design object exists. I see my analyze, generate, and summarize function. So now I can. Okay, hopefully for real. Fingers crossed. There we go. Success. This is where we all clap, we cheer, we do a little happy dance, whatever it is, because we got our simulation working. If it's doing what I think it's doing, remains to be seen. But we see right here is a couple of things. So in the R console, we've got by default to be disabled a progress bar. So we can see for this particular condition, so my design, there's only one row of my design object. Up here, we got one row with 3 variables. And so the current iteration is on is the first design condition out of 1. So if there was 10 conditions, it tells you currently what is on, and it tells you when it started, the elapsed time, so you can get a sense for whether you need to go for 1 coffee or whether you have time to go for dinner and then come back, or whether you can turn your computer screen off for 2 weeks and come back when it's finished. So it also gives me a bit of feedback about the execution time. So 7.39 seconds to simulate 1,000 samples and analyze them and summarize them all for me. And it also told me that it externally saves simulation results to a file with this name. So I see it's got my date and information. And it's an RDS file. So if you're not familiar with .rds, it's a way of taking our object and saving it in a format that you can import it, and it keeps all the structure. So rabbit trail. If you, sometimes when we save data, it's nice to save it in a format that can be opened by multiple different software packages. So if we've got flat or data that's like a table, saving it as a CSV is nice because then anyone can open it in Excel, in R, in whatever statistical software you're dealing with. RDS files, a way of saving things, the binary objects. So when you import them, remembers that certain variables were factors or certain variables were of particular atomic types, so we can keep all that. I'm just going to take a peek at our results here. Okay. Actually, we're going to go to the slides because it's a little bit clearer. Okay, so the object that gets returned back after a successful call to the run simulation can be best understood as sort of 3 distinct pieces, where the leftmost piece is exactly our design object. So you can think about my design object as having 3 columns and a certain number of rows. So my final results object is going to have the same number of rows as my design object, because each design row indicates a current condition, and I'm going to have data that's been summarized or meta-summarized relevant to each particular condition. So I'm going to have the same number of rows as I've got in my design object, and the leftmost columns are exactly all the condition values or levels of my factors for my design objects. We can easily see that certain results are paired with certain conditions right there for you. Then the middle sort of block is going to be all the results we got from our summarize function. So if I just did one variable called EDR like I did today, the next is just going to have one single value, column, pardon me, that's going to be the middle blocks. And on the right hand, or rightmost side, is going to be a lot of extra Monte Carlo simulation implementation information. So if errors were thrown, how many errors were thrown, if there's warnings, whether current runtime, the data is completed, all this extra information that might be helpful to you for debugging purposes, is automatically going to be appended onto the end. And you can actually sort of view that. So I'm going to take a look here. So this is our design condition. Again, we've got mean difference, sample size, variance ratio. And then I've got my results from my summarize function, the empirical detection rate, the number of replications that were run. So I asked to do 1,000. So I see I've got 1,000 times. The simulation runtime, the data was completed, and also the seed that was used to generate that, which is nice. So we're not going to go into today, but you can actually save these seeds, and you can have what's called macro reproducibility. So I can run this simulation, pass in these seeds for generation, and get it, well, I'll say, yeah, exactly the same result again if you needed to run. So you can completely computationally reproduce your simulation experiment by using these seeds that we've saved. And there's also a way of saying, I want to save these seeds externally to another file to make it easier. But it seems that we've got some sort of results. We want to make sure that it's what we think it is. So I'm going to first go to my first design condition. So these results right here, I added a couple extra values. So I've got mean differences fluctuating between 0 and 0.5, 2 sample sizes, 0 and 60, and a variance ratio of 1 to 1, and then sort of 2 to 1, where the second group is going to have twice the variance of the first group. So here's our baseline condition where I've got no population mean differences, sample size of 30, and the variances are equal. And since we generated our data to be independent of each other, we had 2 calls to the rnorm function. We did 1,000 replications. I can see here that on my empirical detection rate, or in this case, my false positive rate, because the population means are actually truly not different from each other, is really close to our nominal 0.05, which means, okay, it looks like how we coded up our generate, analyze, and summarize seems to be performing the way I'm expecting to do it. We can also check what happens otherwise when they're as sample size increases, so the mean difference stays the same between conditions 1 and 3, and variance ratio stays the same between 1 and 1. The only difference now is as sample size increases, my false detection rate actually drops down a little bit, which is a little bit curious to me, but there could be a lot of reasons why, because you'd also have more power with the more sample size. So by doing careful comparisons between our different design conditions, we can sort of see what's happening as we systematically vary one condition and hold the others constant. So there's actually a couple arguments I want to bring to your attention as well for the run simulation function. So one I highly recommend is the save results equals true. And that is immensely helpful because what that's going to do is every time it goes through a condition and it runs analyze function on your 1000 replications, and we've extracted out those results and saves that, but that's what gets passed on to our summarize function. It's going to save those locally within your project. If you're dealing with an R project, it'll save there into a particular directory specified, or by default, the root directory or working directory. And so you can use those later for re-summarizing data. So maybe there's a different summary statistic you wanted to use. But the other nice thing about this is you can, I'll just leave it there for now. So you can actually re-summarize it with the re-summarize function by saying there's a new summary function I want to create that's going to extend the pre-existing one. Instead of rerunning your entire simulation experiment, you can just tell it where to find the saved results, and it'll go over, automatically grab them, pull them in, and re-summarize them using the new function that you defined. If you're after macro reproducibility, you can also do save seeds equals true. So by default, it's false, but you can set it to true, and it'll save the seeds you can use for later. Save details if you want to, say, take the results and seeds and store it into a different directory within your R project or your file. One other really nice thing you can do is, because of the functional separation of the generate, analyze, and summarize functions, it's actually got built-in support for parallel processing. So if you're doing a nested for loop strategy, you can't do those things because there's no way of saying I'll step that back. It might be exceedingly difficult to take that and parallelly distribute all the different processing parts. But since this is functionally separate, it can actually say, okay, so I've got 4 cores on my computer. One is going to be the one that sort of delegates and instructs the other nodes, and it can send off maybe entire conditions off to these other nodes to be run independently of each other, and then that gets sent back automatically to your main node, and then it'll summarize the data for you. So just by saying parallel equals true, you're going to automatically speed up your processing time of any simulation you run, because by design, it can just handle that because of the functional separation. A bit of a note to you that a common error I've encountered myself is when you are doing that distributed processing, oftentimes you might get an error that says, package not found, or function not found, pardon me, or particular objects not found. Because in my global environment, I've loaded particular libraries, but SimDesign might not know that those nodes need those. So what you do is you just have a character vector. So if I use the broom package to use the tidy function, and I'm going to need that in each one of my analyze functions, I can set up a character vector that says broom, or any of these other packages I might need, and SimDesign will make sure that each one of those nodes has access to those libraries, make sure they're loaded, so you're not going to get error flagged for yourself. Super handy. Just can't even talk about that enough. And so another nice feature I want to show you is we're going to hop back over to RStudio for another possibly final time, and I'm going to show you another really nice built-in feature for SimDesign. So let's say, for instance, we still got this, but I want to run 3,000 examples. So I don't have to go back and recreate my design object, analyze, generate, summarize. All I'm doing is increasing the number of replications. So those things will already be existing the way I want them to be. I don't have to make any change to those to increase my number of replications. I just change this argument. And so when I run this particular chunk of code, you can see our progress bar, and it's chugging along, going through there. But then what happens if you've got a power outage and your simulation stops? Most cases, you would have to automatically rerun the entire simulation again because you sort of lost that. So if RStudio encounters a problem because of memory issues or whatever, and it crashes, something happens on your computer, or there's a power outage, it's horrible to have to rerun that all from scratch, especially if you have something that takes multiple weeks because of the complexity of the simulation process, the analysis process you've got. So what another thing I'm going to show you here is part of the bad scrolling, but what if I had a couple of different conditions? So what if I had a true mean difference of 1? So I'm going to redefine this create design object, and I don't have to touch my generate, summarize, or analyze functions. I'm going to hop back down to my simulation. So now when I do this, I should have 2 design conditions. So let's run this again. It's currently going through the first design condition. And it's simulating 3,000 cases, and it tells me I got about 11 seconds, so I get a little bit more time to talk to you. And when it's done, it'll automatically trigger onto the next one. Or if there are particular errors that get flagged, that might also crash these. And we'll have time if I talk about those. So what happens now is if I start running the second condition, so completely finished one of the first conditions, and then I have my power outage. Question is all of this lost? And the answer is no. So by default, SimDesign is going to save temporary results for you. So as it completes a condition, it'll save that for you locally within the directory where your script lives or your R project. And by default, if something happened to the simulation, all I have to do is load up my script, make sure that I've got my design object, analyze, generate, and summarize functions defined here for myself. And if I just rerun the exact same code, it's going to pick up at the condition where I'd left off. So it didn't get all the way through here, but it doesn't have to redo condition 1 because it saved it. And it tells me right here is resuming my simulation using this temporary file that it has a naming convention for. And it'll also automatically remove that temporary file for you because it's no longer needed. And as it completes a new one, it'll save my results. Another thing you might see here is I've got a particular warning because I already tried to create and save my results today using that date, but I ran my simulation 2 times. The second time was to showcase something else. So what it did was it says it detected that that file already exists and you don't want to accidentally write some of the results because maybe you changed something, maybe you added something to the analysis phase or whatever it is, and you still might need the original one in case there's an error in your code. So you don't want to completely lose everything. So by default, it'll check to see if that name exists. And if it does, it'll create a similarly named name and it'll sort of add this -1 at the end of it to make sure that you've got distinct things so you don't accidentally overwrite results. To me, that's amazing. That's just such a good thing to think about. So we're nearing the end of our, by nearing, I mean, we're at the end of our simulation discussion about the sim design package. So I hope you got a lot out of this today, and I got a bit of time afterwards for questions. And these slides, when they are available, there are more talking a little bit about additional features, like how you might start about debugging your simulation, other additional safety features or handy things you might need from the SimDesign. But we're going to wrap it up here today because we are out of time.
So much, Mark. That's really, really fascinating. There's some like really, yeah. When I think about doing doing these kind of simulations, you know, line by line like that, this just sounds like it's going to make it way easier, especially the parallelization element.
Yeah, that's at least the one. I said, at the very least, hopefully, can benefit from computational efficiency.
Yeah, absolutely.
So again, speed isn't our big concern. Make sure you've coded it right, and then.
Of course, yeah, exactly, yeah. So, do we have any questions from the audience at all about SimDesign or more broadly, like simulation in general? Got any questions? You can either hands up or chat box it. Or maybe you turn off the quick link to the materials. Okay, that's just coming. I believe it's coming along later, isn't it? The link to the materials. Yeah. Yeah. I'll turn off the recording now, just so like to make it less intimidating. So thanks again, Mark. Cheers.